For 2 whole centuries, there was a specific kind of math problem that pretty much everyone agreed was impossible to solve. Today, we're diving into a fascinating claim that might just shatter that 200-year-old rule.
So, let's just start with a huge question. Imagine this. What if a mathematical impossibility, something accepted as a fundamental limit for 200 years, was just proven wrong? What if that unbreakable wall that mathematicians built theories around was never really a wall at all?
So, the giant in our story is something called a high-degree polynomial equation. And believe me, for centuries, these things have been one of the absolute toughest challenges in all of mathematics.
You see, the goal was always to find that one perfect formula, a kind of master key that could solve any polynomial. Now, they found keys for the simpler equations, but as they got more and more complex, the locks just became, well, unpickable, or so everyone thought.
And this right here is the monster at the heart of our story today, the 9th-degree polynomial. Any equation with a variable raised to the power of 9 was basically put into a box, slapped with a label that read fundamentally unsolvable, and for 200 years, that box stayed sealed shut. So, you might be wondering, who's the one who shut and locked that box? Well, that brings us to a really pivotal moment in math history, the building of what's known as Abel's wall.
I mean, just look at the sheer amount of time we're talking about here. The 4th degree gets solved way back around 1545. And then, nothing. For almost 300 years, the smartest minds on the planet hit a total brick wall. Then, in 1824, Niels Henrik Abel comes along, and he doesn't just fail to find a solution, he does something much more dramatic. He proves it can't be solved. And for 200 years, that was it. Case closed. The final word. Until now, maybe.
And here is the law itself. It's called the Abel-Ruffini theorem. And what it basically says is there's no single universal formula using what we call radicals, things like square roots, cube roots, for equations that are 5th degree or higher. This wasn't just a theory, it was considered a rock-solid, definitive proof of impossibility.
But you know how it goes. Every long-standing law, every supposedly unbeatable champion eventually meets a challenger. And in this story, that challenger is Professor Mourad Sultan Ezouidi.
And this quote from him really gets to the heart of his entire approach. While the rest of the math world saw a fundamental limit, Professor Ezouidi saw an accepted limitation, and he simply refused to accept it.
Now, this is a really critical distinction he makes. He isn't saying Abel was wrong, not at all. His argument is that Abel's proof was correct, but only within the framework of the math they had back in the 19th century. He's basically asking, what if we build a bigger framework? In that bigger framework, the so-called impossible might just become possible. So what exactly is this new framework? What's the secret weapon that he thinks can take on a problem that generations of mathematicians thought was completely unbeatable? This right here really lays out the massive shift in thinking. The classical view is almost a kind of mathematical fatalism, this idea that some things are just unsolvable, period. But Ezouidi's view completely rejects that. It suggests that Abel didn't discover the edge of algebra itself, but maybe just the boundary of one particular tool. Okay, so without getting lost in the super complex formulas, his method essentially does 3 things. First, he totally reorganizes the equation into these nested layers. Then, he applies a series of really advanced transformations to those layers. And finally, he uses a brand new process to pull out the equation's exact perfect roots. It's just a completely different way of looking at the problem.
And, well, when you look at the problem in a completely new way, you get a very, very different outcome. This is where the claim goes from just being interesting to being truly profound.
This table just lays it all out, plain and simple. On the left, you've got the classical methods, stuck in the mud since 1824, forced to rely on just getting close enough with approximations. On the right, you've got Ezouidi's claim, exact, 100% verifiable, algebraic solutions. The classical outlook accepts that there are limits. Ezouidi's rejects what he calls mathematical fatalism. The potential impact here isn't just solving a problem, it's establishing a whole new paradigm in algebra.
This quote really captures the scale of what's being claimed here. It's not about finding some clever little loophole in an old rule. It's about arguing that the entire playing field of algebra is actually way bigger than we ever thought. So let's say this claim holds up to peer review. What does it actually mean for all of us? What are the implications for the future of math and even science itself? Well, here's why this matters so much. It could kick off a whole new era where we move from just approximating answers to finding perfect, exact ones.
Just think about fields like cryptography or quantum physics, where an exact solution, not just a close enough guess, can be the difference between a secure code and a broken one, or between a stable model of the universe and one that just falls apart. It's a fundamental challenge to a core belief that mathematicians have held for centuries.
And that kind of leaves us with one final thought. The story of Abel's theorem was a story about limits. But the story of Ezouidi's claim is a story about discovery. So if a wall that has stood for 200 years in the world of pure mathematics can potentially be torn down, it really makes you wonder, doesn't it? What other impossible things are out there, just waiting for someone to come along and look at them from a brand new perspective?